Given our definitions of weak stationarity, we have said that important sources of known stationarity are trends, seasons, and structural breaks. Now, together we will see how we can deal with trends and seasons, so the seasonality effect in a time series. We will not cover too much, I will only give some hints about dealing with structural breaks, because this is a rather complicated part of time series theory, and also the number of tests and procedures that we should use is very big and important to be just covered quickly. Now, we will start with trends. We will see that in order to deal with a possible trend in a time series, we have different techniques. The most important ones are linear regression or regression techniques in general. If the trend is not linear, obviously you don't use linear regression, and differencing, that is to say, taking the differences in the data. Before we start speaking about detrending, one important information. This lesson is complemented by an R notebook in which you find some very first analysis about time series. So in particular, I show you how to create a time series object in R and how to perform some very basic detrending that we are covering together in the next minutes. What I ask you is to have a look at the R notebook. It is fully commented, so you find all the details already in the notebook. Detrending is the operation that we perform in order to remove the trend from a time series. Now, the trend can be of many different types. We can have a simple linear trend, we can have an exponential trend, a parabolic trend, we can have a logarithmic trend, we can have a stochastic trend that changes over time, we can have a trend that is deterministic but still changes over time. So there are many possible trends we can play with. Now, why is it important to remove the trend from a time series? Because it is extremely simple to verify that if a time series has a trend, then the first requirement of the definition of weak stationarity is immediately violated. The first requirement is that the mean is constant, is equal to a mu that does not depend on time. But if there is a trend, necessarily the mean will change over time. So it is extremely relevant for us to try to remove a trend from a time series. Consider this very simple example in which a process xt is equal to a constant beta 1 plus a constant beta 2 multiplying t plus a white noise wt. Now, if we take the expectation of this process xt, what happens? The expectation will be just the sum of the expectations of the different components that we can see on the right-hand side. Now, the expectation of beta 1 is just beta 1, because beta 1 is a deterministic quantity, is a constant. For what concerns the expectation of beta 2t, again, what we get is beta 2t remaining there. Finally, for what concerns the expectation of the WT terms, since we are speaking about white noise, the expectation is 0. So that term disappears. So what happens? We have that the expectation of xt is equal to beta 1 plus beta 2 times t. But it is immediate to observe that a very simple linear trend like the one that we are considering here immediately makes the expectation of xt depend on t via the beta 2 times t term. And this is something that we don't want because it violates our requirement of stationarity, of weak stationarity, and then also of strong stationarity. Very often, when visualizing a time series, because please always plot your data, always. Don't start analyzing data without having no idea of what you're playing with, okay? It's a very silly error, even if, unfortunately, very common. Very often in consulting, I see people that start computing things without even plotting once their data. So you have to plot your time series. And very often, if there is a trend, it is evident from this very first plot, from this very first visualization. Maybe it is not completely clear if the trend is linear, if the trend is logarithmic, and so on. So you have to go further, but you can quite easily observe that there is something that may impact the mean of the process over time. In other situations, this is not the case, and maybe you need some extra tools that nevertheless I always suggest to use also to complement a very first visual inspection. So it is not sufficient just to see, okay, there is a trend, and then I try to remove that. Using, for example, the ACF, the autocorrelogram, you can try to have an educated guess about the type of trend you are playing with. If it is just a linear trend, if there is also some seasonality, if it is a trend that changes over time or so. Now, in these plots that you see here, you have a clear example of a time series with a trend, and another example of a time series that does not necessarily show a trend immediately, but that could have a trend and that we have to further investigate. As I told you, the ACF is an important plot that we can use to study a time series, to try to understand the basic characteristics of a time series before entering in the real modeling of the time series. Because we will see that we have different approaches for time series. We can have autoregressive model, moving average models, ARMA models, ARIMA models, SARIMA models. So we have to try to figure out what is the proper model. Now, in an ACF, what do? We just plot the correlation, the autocorrelation function, rho of h, against different values of h. And we look at the behavior of this autocorrelation. Now, if our rho time series, and when I say rho time series, I mean a time series on which we have done nothing, so it's just the time series as we have downloaded that, as we can read it from the data with no transformation, no modification. It's just the original time series. So if the ACF of a rho time series shows a long exponential decay as the one that you can see on your screen, this is typically a good sign of the presence of a trend. Now, when we say exponential decay, you will see that we do not mean that we really have to see all the bars going down on the same part of the plot. We can also have that some of the bars are on the negative side, so for negative correlation, they can also change, having a sort of sine-cosine behavior. Those, for example, are signals of seasonality in the data. But so when we say a long exponential decay, it means that if we consider, let's say so, the absolute value of the autocorrelation, then yes, you should see a long exponential tail in your ACF. But in practice, those quantities can be above or below. What is important is that they are significant. And in order to be significant, they need to be out of the confidence bar that you see indicated in the ACF. Nevertheless, we will use the ACF a lot, so we will have all the time in the world to further discuss on how to read the ACF, for example, when we deal with ARMA models. As we have already said, there are many different types of trends: linear, quadratic, parabolic, logarithmic, exponential, whatever you want. We start by considering the linear trends. This is very important because linear trends are the most common type of trends that you can find in financial time series, so the type of time series that are important for us. The process xt that we have considered before is an example of process with a linear trend. The linear trend is given by the component beta 1 plus beta 2 times t, so we can represent this as a line in terms of time. A linear trend generally indicates a basic accumulation or decumulation process in the phenomenon that we are considering, and this is quite common in financial data. Consider for a second this time series in which we consider the global temperature deviation in the last 140 years or so. It is clear that there is an increase in the values that we observe for our phenomenon, so the global temperature deviation, and this trend is likely to be of the linear type. In fact, we can superimpose a linear trend to the data, and it is clearly a type of trend that we will call linear. The most used procedures to detrend a time series, to remove a linear trend, is to use either linear regression or differencing. Now, these two different procedures will give very often different results. Which one to choose really depends on the type of phenomenon that we are modeling and on what are our ambitions for the modeling. Now, if the trend itself is important for us, so we really need that information later for prediction or whatever, probably linear regression is to be preferred. And linear regression is a little bit more flexible than differencing, in particular when the trend is not linear. You can always fit a non-linear regression if you want. Differencing, conversely, is very strong in removing trends and partially seasonality from the data, and it's to be preferred when you think that the trend in your data is not necessarily deterministic, and maybe it is even deterministic, but it is piecewise defined and you have many different trends together, so in that case differencing can be preferable to linear regression. In any case, my suggestion is to always use both approaches, and only after, when you enter into the modeling, you choose with which one of the two you will actually proceed. Because what you get is that you start from a time series, you remove the trend, you obtain a new time series. So if you apply two different approaches, you will get two different time series. And from there, then you can go on with your analysis. And most of the time, you choose on the basis of the results of the detrending procedure. If you want to detrend by using linear regression, what you do is very simple. You fit a linear regression for the trend, and you will use the residuals of this regression as the new time series for your analysis. So what you do, you fit a linear trend, if you want to fit a linear trend or any other type of trend in your time series, you remove that information, and what remains are the residuals of your regression. Okay, those residuals will be the starting point of your further time series analysis. In the notebook associated with this video lesson, you will actually see how to use simple linear regression, in particular the LM linear model function of R, to detrend a time series. Trend removal by differencing relies on a simple observation. If you have a process xt, for example, the same process we have considered before, that is to say beta 1 plus beta 2 times t plus a white noise wt, then if we define a new process that is defined in terms of first differences, so the new process will be the process xt minus 1, so that after that xt plus 1 minus xt plus 2 minus xt plus 1, and so on. So we define a new process on the differences. Okay, in that way, this process is free from the linear trend that was originally present in the initial process. Now, to verify this is extremely simple in the basic example we are considering, and now compute the expectation of the new process on the differences. What do you see about the mean? Is the mean of this new difference process still dependent on t? If you remember, what I told you is that when we play with financial time series, like for example the price of an asset or so, we prefer not to play with the price directly because the price is bound to be non-stationary most of the times, but we rather prefer to play with the returns or with losses as percentage, depends on which approach you want to consider, what quantity you prefer to be positive, if returns or losses. But why is that? Because returns tend to be stationary, or at least more stationary than prices. The reason is simple. Essentially, when you are moving from prices to returns, what you're doing at the end of the day is an implicit differencing. Can you see that? In the case of a linear trend, the choice between differencing and linear regression is a personal choice, is a matter of personal preferences. Because in case of a purely linear trend, you will tend to obtain the same results. The point is that in reality nothing is pure, so it's very rare to find a purely linear trend. Now, the difference between differencing and linear regression is that differencing tends to be stronger. So it is an approach that tends to guarantee a higher success probability for what concerns finding out stationarity in a few easy steps. And if there is some sort of moderate seasonality with differencing, you can also try to get rid of that. While if the seasonality is strong, we shall see, it is usually not enough to take differences. For what concerns linear regression, regression per se, it's more flexible. You can try to model a lot of different types of trends. So instead of fitting a trend in t, you can fit a trend in t squared, t to the power 3, the log of t. So you can really introduce many different trends in your modeling. And regression can be extremely useful when you want to keep the information about the trend, because it is an important part of your analysis. So you want to know what are the parameters of the trend that you are fitting. While if you impose differences, essentially you are removing the trend, but you are also losing information about the qualities of that trend. Assume now that the process is like the one that you can see on your screen. My question for you is, what happens if you take first differences? Are you able to remove the trend? What happens to the new time series that you are creating? So start from this xt and define the new process yt equal to xt minus 1, and go on from there and try to understand what is happening in applying differences in this situation. Let's go back to the time series of the global temperature deviation that we have considered some minutes ago. Now, the time series is the time series that you can see now on your screen. What I want to show you very briefly, without entering for the moment into the details of the interpretation of the ACF, is what happens to the ACF of these time series if we apply linear regression or differencing. Actually, we get two very different results. With linear regression that you see here on top of the slide, we are able to remove the linear trend, and in fact the ACF is different from the very long ACF we observed before with the original raw time series. But still we see that there is a lot of significant lags in terms of the autocorrelation function. So there is still quite some substantial time dependence in the data that still needs to be removed if we want to understand what is the real structure of this time series. Remember that at the end of the day, we want to be able to remove all the structure until we reach a white noise. Okay, so here for sure we are not dealing with a white noise. There is some time dependence that we still need to model. Now, what's the problem here? The problem is that with linear regression, we are able to remove the linear component in the trend, but for example, we are not taking into consideration any season. And as we shall see, actually, there is seasonality in this data. So it is important also to remove that. And what remains, in principle, is the time series that we might want to model using an ARMA process and any other type of process that we will consider to get. Using differences, on the contrary, you get the second ACF, the one on the bottom of the slide. Now you see that the ACF is actually different. So the number of significant legs in our ACF is substantially smaller, and we could also be tempted to think that we are done, in a sense that all the legs are not particularly relevant, so maybe it was just a matter of having a white noise with a trend, which is not the case. We will see why later. So an ACF like this sometimes can be extremely misleading, so never trust, again, just one plot in your analysis. But you see clearly the difference between the linear regression and the differences. Once again, I repeat, in the R notebook that is associated to this lesson, you will find other examples using financial quantities. So you will see the difference in performing detrending using linear regression or taking first differences. There is one last thing that I want to tell to you, and it's related to the ACF plot. Now, in all the ACF plots that we have considered, if you go back in our lesson, you will see that the first bar is always extremely significant and equal to 1. Okay, but don't be fooled by the plot, because that first bar corresponds to row 0, which is the correlation of xt with xt, so it is trivially equal to 1. Okay, so in reading the ACF, you can completely ignore the first bar and just focus on the bars from h equal to 1, 2, 3, 4, 5, and so on. So don't waste your time on the first bar, and don't be overexcited if you see a very strong autocorrelation between xt and xt itself, because that's trivially the case.